All right, exam 1, physics 202, spring 2016. Rank in order from largest to smallest the absolute values of the gravitational potential energies for these pairs of masses. Now remember, potential energy is G, M, M over R. So I'm just going to take M times M over R for each of these and rank them. So I'll say, for example, here 2 times 2, that's M times M over R, which is 4. So that's equal to 1. Here I have 1 times 1 over 1, that's equal to 1. Here I have 1 times 1 over 2, that's equal to a half. Here I have 1 times 4 over 4, that's equal to 1. And then down here I have 4 times 4 over 8, so that's equal to 2. So E is the biggest one, so that gets rid of this one, this one, this one, and this one. And then the next are A, B, and D are all equal, so that's this one, and then C is the smallest. All right, so that leaves A as the only right answer. Escape velocity of an object in gravitational field can be determined using which of these? So remember, on the surface of the Earth, when I have a rocket that's taking off, it has a total energy equal to 0, and that energy is made up of U plus K, the gravitational potential energy plus kinetic energy. At the bottom, when it's here, it has no gravitational potential energy, and so you have to give it all kinetic energy in order to escape. So that is the law of conservation of energy. The planet has the same mass as Earth, but 1/2 the Earth's radius. If the gravitational field on Earth is 10 meters per second squared, what is the gravitational field on this other planet? Gravitational field, that's just fancy way of saying the acceleration due to gravity, so it's gm over r squared. Remember, this is taken from equating mg, the force weight equals mg, equal to gmm over r squared, and solving for this, and you get this expression, where the big M is the mass of the Earth. Now, if I make the radius, the mass is the same, but I make the radius 1/2. That means I'm going to 4 times the acceleration due to gravity. So here, where it was 10, it's now going to be 40. So that's number 3. The value of g at the height of space shuttle's orbit is, so this is a lot more than the Earth's radius. So our acceleration due to gravity is going to be much less than 10 meters per second squared, but not 0. Two masses experience a gravitational force. If you double the distance between the objects, what is the force? Well, this is gmm over r squared for the force. This is Newton's universal law of gravitation. If I double this distance, that means I quarter the force, so 1/4. A gravitational field is a measure of force per unit mass. Sorry, that A should not be there. The up quark has an elementary charge of plus 230, down quark of minus 130. What combination of 3 of these quarks makes up a neutron? Well, a neutron has no charge, it's neutral, and so the sum of the charges, if there are 3 of them, have to add up to 0. So I have plus 2/3, but I have to have an up quark. Then I also have to have a minus 1/3 and another minus 1/3. So that is up, down, down. So B is the right answer for number 7. Okay, you bring a negatively charged rod near to a neutral copper wires in this figure. Which of these statements is true? Well, this is what's going to happen. The negative charges are all going to rush down here, leaving me with positive charges here. In that case, the wire will be attracted to the rod. So A is not right, it's not going to move away. Negative charges will move to the right-hand side of the wire. Okay, that's true. Nothing will happen. Oh, that's not true. Positive charges will move to the left-hand side of the wire. We say, gosh, that might be true. Let's come back. Negative charges will move to the center of the wire. That's not true at all. So what about this one? Why? The answer is B, it's not D. So why is that? Well, it's because the positive charges don't actually move. The positive charges just remain on the left-hand side. So you get this excess of positive charge, but it's not because of any transfer of protons. In a conductor, it is not the protons that move, it's the electrons. Imagine 2 charges, A and B. Charge A is attracted to a positive charge. That means charge A must be negative. Charge B is repelled from a negative charge. That means charge B must be negative as well. What happens if you bring A and B? Well, you have 2 negative charges. They're going to repel. It's number 9. Doug rubs a piece of fur on a hard rubber rod, giving the rod a negative charge. What happens? Okay, well, I have this rod and I have this, fur over here. I rub it onto the rod, leaving a negative charge on the rod. That means that electrons have gone from the fur and they've gone onto the rod. That means that I must have a net positive charge on the fur because I've lost electrons. So let's see. This is not true. This is not true. Electrons are added to the rod. That is true. D is not true. Protons are not removed from the rod. So 10 is C. Two electrons and a third charged particle are located at different positions along a straight line. Both electrons experience zero net force due to static electricity. Is the charge on the third particle positive or negative, and where must it be located on the line relative to the electrons? This is a little tricky. All right, so I have two electrons all along a line, and then I have a third particle, and I want to know, both of these electrons have zero force. F equals 0 for this one, F equals 0 for this one. I want to know where is the other charge and what is the charge of it and where must it be. Let's just go through each of these. So for A, negative in between the electrons. Well, if I have a negative charge here, let me spread these out a little bit. I'm going to put my electrons here and here. And then let's say I have a negative charge, I put it right here. What would be the force on these charges? Well, on this one, it would repel from this negative charge, and it would also repel from that charge. So it can't be A. Positive in between the electrons. Well, let's see. I put a positive charge there. The charge on this electron due to the positive charge will be in that direction. Due to this electron will be in that direction. Okay, so far so good. On this electron due to the positive charge will be in that direction. Due to that negative charge will be in that direction. Okay, yeah, it could be 0. So let's go ahead and mark that one. Let's just go ahead and look at the other two. But the answer is B. Negative with both electrons on the same side, so I have a negative charge over here. Okay, with this charge, this charge will be repelled from my negative charge over here, and it's also going to be repelled from that other negative charge. So okay, that can be 0 force. But let's look at this one. It'll be repelled from both of those negative charges, so that one will not have a negative charge. And finally, let's look at this fourth one. Well, let's went into this. Positive with both electrons on the same side. Positive. Okay, so attractive, repelled from that negative charge. So that one doesn't get a 0 force. This one over here could possibly get a 0 force. It is repelled from that electron and attracted to the positive charge. So not D, B has to be the right answer. This diagram shows 3 heavily charged plastic cubes. And then there's a force on cube 3. What are the charges? Well, in order to get this force, I have to have forces that are in this direction and this direction. Excuse me. This is a positive charge. That means actually, hold on, let me see. That's not right. Let me redraw that. In order to get this, I'm going to have forces that are in this direction and in this direction. I apologize. And if this is a positive charge, that means that it's going to be repelled from this charge, so this has to be positive, and repelled from this charge, so this one also has to be positive. So both of them are positive. That is B. The force between two charges, which are separated by 4 meters, is 12 newtons. What if I bring them closer to 2 meters? All right, well, this is K, Q over R squared. If I have this, I'm going to have 4 times the force. It was 12 newtons, now it's going to be 48 newtons. This shows 2 metal spheres. Q2 has 3 coulombs. You can tell by these that it should be negative. If you can't see that well on your test, I'll make a point to it. So it is a negative because the field lines are ending in the charge. That means that this has to be positive. If you count these number of field lines, it has twice the number of field lines, so therefore it must be positive 6 coulombs. Electric field is a measure of force per unit charge. We had a very similar question for gravitational field, which is force per unit mass. And then here, at what point is the electric field equal to 0? Well, over here at A, you just want to draw your vectors. Due to this plus 2q charge, I'm out of a force in this direction. Due to the plus 4q charge, I'll have a smaller electric field in that direction. Remember, I said force, I mean electric field. I'm imagining that I have a positive test particle there, and I ask myself, what is the direction of the force that that positive test particle feels due to those other charges? And then that will tell me what is the direction of the electric field. Okay, let's go ahead and do E over here because it's not E either. A is not the right answer. E is repelled from the 4q charge, and then it gets a little bitty electric field due to the plus 2q charge. Okay, now let's look at these others. Due to the plus 2q at point B, I get an electric field in that direction, and I'm further away from the 4q charge, so I get an electric field in that direction. It will turn out that B is the right answer, as you can see, but let's look at these others and show that it can't be those. So C here, I'm equidistant between these two charges. I'm going to have a big electric field due to this one, and one that's half that magnitude due to the plus 2q. So that one will have a net electric field to the left. And then finally D, I will have a big electric field due to this plus 4q because I'm closer to it, and then just a little bitty electric field due to the plus 2q because I'm further away from it. So it can either be C, D, or E as we showed before. So B is the right answer. Draw the field lines to represent the electric field. Okay, so I'm looking for two things. One, that you get the direction of the electric field lines correct. They should look like that. And then also that you get the number of electric field lines. So bare minimum, you have 2 electric field lines here, and then 2 field lines that go out. As long as you had twice the number of field lines coming out of the plus 2q charge, and then half of those field lines going into the minus q charge, because I have a ratio of charges of 2 to 1, I should also have a ratio of electric field lines 2 to 1. Okay. Here you're supposed to find the electric field vectors at point A. You find the magnitude and direction, and then a couple other questions about the electron at point A. So let's see, the electric field, just drawing. Let's make that my coordinates. And then I can draw my electric fields. Due to Q1, I imagine a positive test particle there. I will have a electric field that is to the right. I'll call that E1. Due to EQ3 up here, which is negative, it's going to be in this direction. I'll call that E3. And then due to this this Q2, it's going to be down in this direction. I'll call that E2. I can go ahead and find the magnitudes. No, I'll hold off on finding the magnitudes. Let's go ahead and figure out our direction. So I'll need to know what is this angle. That angle will be the same as this angle because these two angles are opposing to one another. I can do the inverse tan of 4 over 3. This is 4, this is 3, as it says up here. That's equal to, if you're not certain, that's equal to 53 degrees. You can do that inverse tan. So this is 53 degrees right here. So now I can draw my vectors. I'm going to go ahead and resolve them. I have E3 right here. I have E1 right here. I'm going to have E2 cosine of 53. And then I'm also going to have E2 sine of 53. Let's go ahead and find the magnitudes of E1, E2, and E3. E1 is equal to KQ over R squared. It's 9 times 10 to the 9th. That's K. Q is 9 times 10 to the minus 9 over the distance between that point and particle 1, which is 3 squared. So that cancels there, there, and there, and I'm just left with 9 newtons per coulomb. E2, 9 times 10 to the 9th. What is Q2? 50 times 10 to the minus 9 divided by this distance, which is 5 meters. Square root of 3 squared plus 4 squared equals 25. The square root of that is 5. So that's 5 squared. Cancels, that's 25, so it leaves me a 2 up there. This is equal to 18 newtons per coulomb. And then E3 is 9 times 10 to the 9th, 16 times 10 to the minus 9, divided by 4 squared. Cancels. That leaves me 9 newtons per coulomb. So those are my magnitudes. I'll be looking that you get those magnitudes correct. I can put those in up here and make these numbers and redraw my vectors. I was expecting to see that you draw this diagram, but you don't have to do all these other vector diagrams with the resolved vectors. But I did ask specifically to draw the electric field vectors on point A, so I'll be looking for that. So now I can draw my, add it up. I'm going to sum up all the electric field in the X and sum up all the electric fields in the Y. I'm going to get this. I'm going to have in this direction E1 plus E2 cosine 53, and that's going to equal to 19.8. And then over here, I find out that this y component of this E2 sine 53, that it is bigger than the positive y component. So I'm going to get here E2 sine 53 minus E3, and that is going to equal to 5.38. So now I have two vectors. I have 19.8, 5.38, and I want to know what is the resultant vector, and I want to know this angle. I'll call it theta, and I want to know the length of this electric field. So the magnitude of my electric field is going to be the square root of 19.8 squared plus 5.38 squared. And that's equal to 20.5 newtons per coulomb. And then I also want to know the angle theta is the inverse tan of my y over my x components. That's 5.38 divided by 19.8. That's 15.2 degrees below plus x-axis. All right, there's some other parts to this problem, but actually I'm going to leave this go because this was in another problem later in the class, later in the test. I'm going to leave out part C and D. Consider this configuration of masses. The mass on the left is a point mass. The one on the right is a spherical shell of mass of radius r. The two masses are separated by a distance d. At first I want to write an expression in terms of the variables above that give the force between the two masses in this figure. So for part A, this is supposed to be really easy, that the force between them is equal to g times the mass of the point mass times the mass of the shell divided by the distance between them squared. All right, this is just the universal law of gravitation, but you need to realize that that shell is considered to be a point mass by the shell theorem, which was part B. You're supposed to describe in a few sentences, 1 to 3 sentences, the shell theorem, which Isaac Newton proved back, in the 18th century. See, I need to pause this for just a second. Okay, and the shell theorem, good wiki page here, and this is the basic idea that a spherically symmetric body that is a shell of mass affects external objects gravitationally as though all of its mass were concentrated at a point at its center. There's some other results from the shell theorem. We didn't really go into those, but you can read them here. And then we did talk about this, how he proved the shell theorem was that he had this shell and he integrated over the surface of the shell and showed that the force at a mass here is equal to this GMM over r squared, which just is the universal law of gravitation. So that shell of mass looks to the outside particle like a point mass. Couple sentences about that. All right, so let's look at this. You find a very large flat structure in the early universe. You're observing, you find this very large flat structure. You find that it has a mass density of 2 times 10 to the 12th kilograms per square meter. We haven't seen mass surface density yet, but I do define it here. It's just a measure of mass per area. I want you to write an expression for the gravitational field above this structure. What is the acceleration due to gravity at a point 1,000,000 meters above that structure? And then if you go a distance twice as far away, what is the the gravitational field? Does it increase or decrease by a certain amount? All right, so first part for A, we need to go to our Gauss's law, which is that the flux is equal to negative 4 pi g times the mass inside our Gaussian surface. The flux is equal to g times our area, which is negative 4 pi g times the mass inside our Gaussian area. I'm looking for the gravitational field, which is g, so this is going to be negative 4 pi big G mass inside. I'm going to go ahead and put in a little 2 here. We talked about this in class, but twice the area, because we have this flat structure, and then we create a Gaussian surface that's also a flat structure above and below. And so we have twice the area above that sheet and below that sheet. And then the flux that is going through that Gaussian surface has to equal, this is our flux, twice the area, because I have 2 sheets, has to equal this negative 4 pi g mass inside. And remember, the negative is because if we think about our gravitational field lines, they're always going towards the mass. And so our gravitational field has a positive value. All right, so notice here, this is our sigma, and so we get an expression, and I can cancel out a 2 here. We get an expression for the gravitational field of negative 2 pi g sigma, which is my mass surface density. It says, what amount of mass per square meter do you have? So that's A. And then B, I want to know, what is the acceleration due to gravity at a distance of 1,000,000 meters. So I'm just going to use that, negative 2 pi 6.67 times 10 to the minus 11 times 2 times 10 to the 12th. That's my mass surface density, and that is equal to 840 meters per second squared. And then finally, see, how does this change? If you change r, well, g is not proportional to r. So that means that g will remain the same regardless of how far away you go. Which is kind of counterintuitive, because, you know, we live in this spherically symmetric world where the acceleration due to gravity decreases as you go up. Imagine this. This is our Earth. Our gravitational field lines are like this. The field lines are close together here, farther apart here. As you go farther away, then the acceleration due to gravity will decrease. However, if we lived on a flat structure, this is a nice argument, by the way, against those who think that the Earth is flat still, and there are still people that believe this. The field lines in this case look like this, and so as you go far away from this, the field lines don't change. They still remain straight and parallel. Now that assumes that you have a very large flat structure, but this is seen here. You're seen even at low altitudes where the field lines begin to diverge and your gravitational acceleration decreases. Okay, one more. This was straight from the homework, so hopefully if you were good on your homework, you were good on this. I have these beam of electrons. They're traveling through these 2 plates. I want them to go such that they just miss the top of that plate. You use this in a lot of different places. Mass spectrometers, inkjet printers use a similar setup to move charged particles of ink where you want them to go. So a similar setup where you use electric fields to move charged objects. The first thing we want to do is figure out what amount of time does it take to get from here down to here in the x direction. It's traveling with an x velocity of, what's that, 20,000 meters per second when it comes into this electric field. And so I know that speed is distance over time. I can find that time, which is going to be distance over my speed. It travels a distance of 0.5 meters divided by my speed, which is 2 times 10 to the fourth. And that gives me 2.5 times 10 to the minus 5 seconds to go from here down to here to move in the x direction. Then I want to know in that time what must be the acceleration so that it moves exactly this distance. So my y displacement is going to be half of 0.1, which is going to be 0.05 meters. It has to do this in this time of 2.5 times 10 to the minus 5 seconds. And so what is my acceleration? Well, I know y is equal to 1/2 at squared. Notice I've left off the v0 term, and you might be asking, gosh, it has an initial velocity here when it first enters the electric field. Why do I leave off the v0? Because when it first enters the electric field, v0 y is equal to 0. So a little throwback to our projectile motion days. Solve this for a. 2y over t squared, which is 1.6 times 10 to the 9 meters per second squared. That's my acceleration. I know that F is equal to QE. I also know that F is equal to MA, so I can say QE equals MA and solve for the electric field, which is really what I know anyway. That's going to be MA over Q. Mass of a proton is 9.11. Acceleration I've already found. And the charge of an electron is 1.6 times 10 to the minus 19. Notice I'm leaving the sign off there. This gives me the electric field, which is 9.1 times 10 to the minus 3 newtons per coulomb. That's the magnitude. I also want to know the direction. My force, if I have an electron here, the force is in this direction. Because this is a negatively charged particle, in order to get that force, my electric field has to be in this direction. Really nice way to move charged particles around. You can just move them between two charged plates. It's really easy to vary the electric field with a simple circuit and make your charges do whatever you want them to do. That's the end, I think. Yep, there's the multiple choice answers. The score breakdown was there were 60 points in the free response, 30 points in the multiple choice, and then of course you had that derivation, which is worth 10 points.